So, hi, hello everyone, hello and welcome. Microbehunter here. Welcome to another Saturday live stream, Saturday microscopy live stream. Yes, what you're able to see over here on the side, over there. Okay, yeah, these are forams, foraminifera in darkfield, and what I would like to do today is a little bit difficult to explain. I would like to explore a little bit the effect of different mounting media on the image quality a little bit, and whether the specimens are then also suitable for the different imaging techniques. It's a little bit difficult to understand here, but what I would like to do is I would like to also try a little bit of oblique illumination and dark field microscopy. So that's kind of a little bit the loose topic that I have for today, and I already see that yeah, people have already started to join the chat. Wow, okay. Yes, hello all around the world. And I see that I'm even being greeted in Esperanto. It's also one of my other hobbies that I have. Yeah, and I also hear that the sound is good. Okay, and I'm very happy that everything seems to be working. In case there is a problem with the live stream, which happened already some time ago, for whatever reason, all of a sudden the live stream was interrupted, and I will try to restart it possibly under a different link. If you have any microscopy related comments or questions, please feel free to post them, and I will try to answer them, but please do indicate it a little bit at Oliver or at Microbehunter in the front so that I know that the question is directed to me. So what I would like to do first is I would like to give you a little bit of a background information here. You probably already know that I have a microscope which is able to use DIC, differential interference contrast. It's a pretty fancy technique, but the DIC microscopes, they give very beautiful, colorful images, and also a little bit of a three-dimensional view. Even though it's not really three-dimensional, but it kind of appears like that. But it is possible to imitate this a little bit by using appropriate filters. And what I would like to do a little bit for maybe 10 minutes or so to give a little bit of a theory, section here. And then I prepared a couple of slides here as well. What I've got here is I've got a condenser with a filter holder. And yeah, and what you can do here, by the way, the filter is blue because many microscopes which have halogen light, because halogen lamps sometimes are very red, the filter removes a little bit the infrared and the red component to give it a more balanced color. And you can also place filters in here. And what I've got here, this is a so-called a dark field filter, a dark field patch stop. You can see that it's a little too small for this one over here. And I've actually 3D printed several of those as well over there in the other box, yeah, which can be placed in here. When you add a dark field filter, then you will actually get an image that looks like this. It's a bright image on a dark background, but not always. And that's a little bit the point of today's video is to show you a couple of specimens where this works very well, and also a couple of specimens which are totally not suitable for dark field microscopy. Okay, so yeah, so this is basically yeah, many microscopes also have a so-called a swing out filter holder where it's not push on like over here, but actually it can be, yeah, it rotates out like this, and that's what I actually have on the top here. So this is not my the microscope that I normally use, but it's a different one that I set up. It's a yeah, relatively a decent microscope. It's the Swift SW380T. I've already made some review videos about that, but you now see that there is now a little, yeah, plastic filter holder that you can rotate in and out. And currently I placed a little filter in here, a dark field filter, and I'm just going to take it out, and here it is. Okay, so it's also possible to make your own, and I am currently in contact with another one of my viewers, Hadrian. Yes, I see that he's also in the chat, and we are now in contact with each other, and because he is also making so-called Reinberg filters, and that's also one of the things that I would like to present in one of the future episodes, which are colored filters which can be made by using foil, which are used for how do you call that? Lamps that are used for stage illuminations, for example. Okay, so if you need a very strong lamp in a certain color, then yeah, there are some foils that colored filter and colored foils that can be used. Okay, so this is So this is basically the thing here, and I basically what I'm going to be doing is it's a little bit of a challenge. Of course, some of you already know a little bit more about what I'm talking about here. Some of you less, but please, in any case, do feel free to ask any questions. Okay? And I already see that there is a question: if you place a dark field patch, do you leave the blue filter in place or do you remove the blue filter? Well, in this case over here, what I have here, this already has a built-in blue filter and it will stay in place because this blue filter will not make the image really blue. It will simply give it a more balanced color because the red component of halogen lamps is quite strong. It simply will remove that, so the image will not look blue if you include that. So essentially, it just stays in here. Okay, I know that many LED microscopes these days also come with a blue filter. I don't really see a point so much in that because LEDs already have a more balanced light spectrum. But for halogen lamps, a blue filter actually is quite good to have because it also removes the heat radiation, the infrared part, which actually causes the specimen to heat up. Okay, so basically I'll just put this in here and then we're ready to go. And what I would like to do now is I would like to now show you some of also some other 3D printed filters that I've made. So I used a 3D printer to make those, but actually I think it's not necessary really. You can also of course use colored foil, and I would like to simply show you now a couple of specimens that some of them that kind of work and some of them that actually don't work at all. Okay, I've put some here, and then I've got a couple of pollen over here which I used with different mounting media, and I would also like to observe those using different techniques, and then of course we can also use DSC to compare this. So basically up here you can always see what I'm doing, right? So I'm kind of rotating out the filter now, and I'm going to just switch over, and what you're able to see already here, that's the view that, where is this now? Oh, I took it out, okay. So let's put this filter here, this one over here, back in again, okay. That's basically the image that we just had, right? And generally, if you might notice one thing, you might notice that the depth of field is fairly low, right? And the reason is because you have to open the condenser all the way. So look also up there again. So this is the lever, that's the condenser, and look, when I close the condenser, of course everything becomes much darker. Okay. Yeah. I also wanted to tell you another little technical detail. Currently, I've got a DSLR camera connected. You might already know that I also have a USB, those USB microscope cameras, right? But there is a reason why I'm not using this. One of the reasons is that it's not quite as light sensitive as my DSLR. And the second thing is that there is no easy way to adjust the exposure time. I mean, I have to go into the software and adjust it. And this takes quite a bit of time. So look what I can do. Just watch what I'm doing. There's a little wheel on my DSLR. And just by turning the wheel, I'm quite easily able to adjust the brightness of the image, and that's the reason why I've actually connected the DSLR camera. Okay, so it's actually for how do you call this, convenience. Yeah. So these are forams. Okay, these are single cell. These are basically silica shells and they work very well in dark field. Okay, and the reason is because they have a large difference in refractive index to the surrounding. So look what happens if I now open it up a little bit. Okay, I open it up a little bit, I'm rotating it out. Of course, it becomes very bright. Okay, so I might want to turn down the light intensity a little bit. I can refocus a little bit. But you might now see a little bit that it looks, the shape looks a little bit different, right? It looks like there is a little bit of a shadow. It looks a little bit like three-dimensional. And this is referred to as oblique illumination. I have to tell you that it looks way better if you look through it under the microscope directly. But currently the image is not quite as clear and as crisp. And the reason is because the camera resolution, which is sent out over USB, is not quite as high. So it's not full HD that I have. It's a fairly old camera. So it does look better if you look directly through it. Okay. There are a couple of other questions here that I would like to go through here. Okay, thanks for taking this topic. Do you have any experience with adding filters to the Olympus CX31? The manual says place a 45mm filters in the light source, which doesn't work. Normally, I mean, the CX31 is the infinity version of the Olympus microscope, basically, normally you put always the filter directly into the filter holder close to the iris diaphragm. Okay, if you put it directly on the lamp, then I don't know if this is always going to work because it's actually quite important that that's placed in the correct position. Yeah. So unfortunately, I do not have any experience with that, but I'm quite sure that it would work. But the really important thing is when using those filters is you have to really make sure that the size of the central disc is correct. And you probably one of the easier ways to figure that out is by trial and error. Okay. Another question is, for what software are you using for live viewing the DSLR on the PC? There is a free Olympus driver. It's the webcam Olympus webcam utility. It's called. Yeah, I think it's webcam utility or something like that. And that is a free software that can be downloaded, and then you can connect the Olympus camera, the Olympus DSLR, directly to a computer, and you can basically import it into the program, or you just use the DSLR as a webcam. Okay, so that's fairly easy. And it's pretty straightforward. Yeah. Are you going to paint your homemade slide box? That's the one over here. Okay. I haven't done this yet. I've made 3 of those slide boxes using a laser cutter, and I still want to spray paint those, but haven't gotten around yet. Okay. So I just also want to show you now the whole thing a little bit using my 4x. Yeah. So this is, let's make it a little bit brighter, other direction here. Yeah. And if you use auto exposure, it's not going to work. Then the forms are going to be overexposed. But what I would like to do now is I'm going to now exchange this and let's take it out. By the way, there's another funny thing here. I've now removed the filter. Look what happens because the plastic holder itself of the filter holder. Look, so it's completely empty now. Okay, you see, it's empty. Yeah, but even the plastic. Itself actually works like a dark field. It's kind of funny. You don't even need a dark field filter. It's actually just if you just use the empty, and if you switch it over like this, you're right on the border. You're actually getting some a little bit of oblique illumination. Need to tune it down a little bit. See, actually that's quite a nice one here, and I'm not using any filter right now at all. It's just a completely empty filter holder, with the borders, the edges, so to say, now in the light path. And look, this actually gives you a 3-dimensional view as well. Yeah? It's kind of a little bit, ironic. I spent so much time figuring out the correct size of the filter, and then all you do is you just put the empty one in here, and you also get a view. I have never tried it with a 40x. Yeah. Okay, so that's now the 40 times. Of course, the depth of field is very low. Okay, so it's no comparison to. Yeah. So there's another thing that I kind of want to show you a little bit, and that is I would like to now show you one of those blue ones that I'd like to put in here. Yeah. Yeah, and here I have to open it again. There is again the problem: the camera is not able to capture. Where is the lever? Here it is. Okay, I have to find it a little bit like this. I have to go up with the brightness, other direction, and then you can basically see the whole thing with a slightly blue background. So you can also imitate some of the videos that I make using my DSC microscope. I also have a blue background to imitate a little bit the water. Okay. So that's also something that one can play around with. So those 4 amps work quite nicely. Okay, I'm going to show you another example that works quite nicely, and they seem to be marine diatoms. Okay, so diatom shells are also made of the same material, silica. And these are many diatoms. It's more blurry than actually when you look directly under the microscope. Yeah, so the image quality is not quite as satisfactory. Yeah, unfortunately. Yeah. But here again, you're able to see a pretty big contrast. You know what I'm going to do again? I'm going to exchange it with, I think it was, let's take again the dark field filter. Fitting it in here is a little bit of a challenge. I think that's the wrong one. That's the wrong one. I use this here. So, yeah. And yeah. Of course, the contrast is higher. Dark field does have the disadvantage as well that it is very dust sensitive. So any dust or dirt or contaminant in the light path will actually start to shine up. Okay, so the question is now, why is this actually bright on a dark background? The reason is because there is no direct light able to go into the objective. It's only the reflected or refracted light from the specimen. However, I would now like to show you a couple of other specimens that do not work. Okay, and these are basically Cyclops and Daphnia. So I'm going to first show it to you in bright field. Okay, and the reason is because the difference in refractive index is not high enough. Yeah, everything is a little overexposed now again. Okay, I have to maybe just find it here using my low power, and yeah, maybe I have to see where it is. No, that's not one. I'm going to, for easier focus, I'm going to close the condenser. Okay. I have to find it, just a second. Here is one, okay? So these are water crustaceans. It's a permanently mounted commercial slide. The specimens were stained, okay? So, yeah, it's basically some water fleas, right? And, of course, I think they're always more interesting alive, but difficult to observe when they're alive because they're moving around so quickly, okay? So what I would like to do now is I go again to my 10x. This is how it looks like. It needs to go up with the light intensity so that there is less grain in the image. Okay, I'm now closing the condenser more. Okay, so that's how it looks like, right? Now let's try to see how this looks like with a dark field filter in place. Okay, so I'm going to rotate this in. I'm going to open the condenser, and what do we see? Nothing. Okay, so I'm actually going to, I hope I'm turning this into the correct direction now. Okay, and let's go up with light intensity. Yeah, so that's how it looks like, and it's not really very interesting or nice. Okay, so why is that? And the reason is that because of the mounting medium used, the difference in refractive index is not so high. So the specimen does not redirect the light so much into the objective, right? So I really had to turn up the light very much and had to go up with the exposure. But you see, there is not a lot of difference. And now even the background is much brighter as well. Huh? So this is a little bit the thing here. The white dot that you see on the bottom, that's the eye. Okay, yeah. So this is the thing which I just want to illustrate to you, that the dark field is not always suitable. Okay, so I'm going to read again a couple of questions here. Is it correct that the light in oblique contrast hits the sample at a different angle than when it creates? So that it creates a 3D effect? Yes, it's like this, that in oblique illumination, what happens is that because I'm kind of decentering the filter, the light only strikes the object from one side, and this creates a shadow, so to say, and this gives the illusion of a certain three-dimensional appearance. Yeah, and this can actually be used to increase the contrast. And I read somewhere that back in the day, in the 19th century, when microscopes did not have quite the resolving power, apparently, this is some of the microbiologists at that time liked to use oblique illumination to look at bacteria, because then you could actually see them much better. Yeah, so it is actually a very old technique, and has been already around for quite some time. I have a Swift microscope. Haven't been using it much lately, but I have a software that came with the manual called Swift easy view. Unfortunately, I don't know that. Sorry, no, I do not have any experience with that. And why is there a software? I suppose it must be the software for the camera. Okay, but it could be that maybe it is simply branded, because many of the camera software is actually the same software from TubeTech. That's the name of the company, and then sometimes the companies actually are when they sell the camera, they kind of rebrand the software as well. Okay, yep. I'm just reading again. Okay, so so that's basically to illustrate a little bit the example when a specimen does not work quite as well. I would like to show you now another one, a cross section of maize, which is corn. Okay, here again I have to kind of find the place, and here we are actually also. You see, it's a similar situation. These are the cell walls, but it is not quite as as easily visible. So I'm going to open it up again to allow a little bit more light in. So you see that the background also starts to light up, and maybe we're able to find again the Let's turn it down again a little bit, and we can also see now. It's right now at the border, maybe not quite as evident as before, but you can also see now that that one side of the cell wall is actually much brighter than the other one. So again, you get a little bit the impression of a three-dimensional view. Yeah. So this is a little bit the thing that I wanted to show you, but again, it doesn't really light up quite as nicely as some of the other specimens. Yeah. And this was kind of the starting point for me, where I said, it's okay. Evidently, the difference in refractive index between the specimen and the mounting medium is quite important. Obviously, it is, right? And so what I decided to do there for today in the morning, so around 12 hours ago, morning from my time, right now where I am, it's in the evening. I decided to use some pollen that I collected some time ago, and I tried to use different mounting media to mount the pollen, to make permanent mounts. And I was kind of then trying to figure out how the pollen looks like in darkfield. It's was kind of a little bit the idea to see if some mounting media actually result in a better dark field impression than others. So this kind of was the idea, and I have to tell you that there was not a huge difference, but there was one difference, in that is that some mounting media actually did change also the appearance of the pollen around, and so that's also something that we can observe. I would like to also do that not only with the microscope that I have now here with the dark field, but also with my DIC microscope. Okay, so I'm going to pause again for myself, and I'm going to look again if there's some questions, and I can see things moving. The question is, how do you know if the tiny things are alive or if it's Brownian motion? So the question is the following. That's a good one, and you're not going to like my answer. So I'm going to read this out. Lawrence says the following: I was looking at a plant cell walls the other day, and I can see things moving when I zoom in close. And my question is how do you know if the tiny things are alive or if it's the random Brownian motion? Generally, if it is a random Brownian motion, then it's really random. Yeah. So particles that are moving random, and very often if you look into a cell and if you look at vesicles moving, then often there is a directional movement because those vesicles are being pulled around. But the thing what I say is why you wouldn't like my answer is because it doesn't matter which one of those, it's not considered alive. And now I know I'm a little bit very detailed, because according to the cell theory, parts of a cell are not, per definition, not alive. So even if these are tiny vesicles, which are actually part of a cell, of a living cell, those vesicles on them are not considered alive. Only the whole cell is considered alive. I know this is a little bit of a playing around with definitions, yeah, but yeah, I just had to think of that. Okay, so what I'm going to do now is we're back here again. I would like to now show you, just for a change. No, let me switch over to the desk first. I just want to give you a little overview of what I've got here. All of these are pollen grains, and I'm just going to run you through. This here is pollen. It's mounted in UKIT, which is a resin-based mounting medium, hydrophobic. Uperol, many of you already know. It's also one of my favorite ones, usually used for mounting insects. Okay, this here is a dry mount, basically mounted in air. So the pollen in here is in air. The blue ring is, of course, I made with a slide ringing table to keep a little bit of a distance here. This here is starting to become my favorite one. It's PVA glue. It's this one over here. This glue is water-based. And I think this actually works very well because it retains the natural shape of the pollen. And this is nail polish, which is the worst one because it likes to shrink a lot. And this here is mounted in pure glycerin or pure glycerol. So you see it's a tiny drop there. All of them are pollen. And now let's have a look if based on the mounting medium present, there is a difference in image quality, and then also, of course, using the dark field and whatever. Okay, I just need to forewarn you, the difference is not going to be too big. However, there are a couple of other things that I would like to mention here. Okay, yeah. So again, interesting answer. Yes. So that's the cell theory actually has 3 parts. The first part says all living things are made of cells. Second part is cells can only come from pre-existing cells. And the third part of the cell theory is the basic unit of life is the cells. Basically means that any components smaller than a cell per definition are not considered alive. Okay, so I'm going to start off with this one over here. And I'm going to now go over to the other microscope. So this one that you see up here is not valid anymore. Okay, so it's my other microscope that I have. And this is now mounted in pure glycerin, so it is not a permanent mount. Okay, and let's go here. Need to adjust everything, and this is how it looks like. Okay, and let's open it a little bit. Yeah, and I can of course change the appearance here, but you see that the pollen grains kind of look kind of dark. Okay. Yeah, on a brighter background. And the reason is that, at least for this technique over here, I have to turn up the light and then it becomes a little bit transparent. The pollen, they do absorb quite a bit of light. Okay, so this is at least how they look like. I just wanted to show you now how the shape of those pollen grains is like. Okay, see that there are 2 parts of it, and that does become a little bit important because we're going to see that in the different mounting media, the shape looks different. Okay, and the reason is because this is this is glycerol. Okay, but some other mounting media will actually cause a shrinking of the pollen. Okay, so this is now in pure glycerin. And I'm just going to add now the second slide here, which is UKIT, which is a resin-based mounting medium, only to be used if you all have fresh air. Okay. And this is how it looks like here. And you see, same pollen, same sample, but look how different. It's an air bubble, by the way. Yeah. And over here. Okay, again, let me just change it to a different color if you want to. Yeah. So maybe like this a little bit. And over here. Look how different it looks like. Yeah. And what we see here is the following. If you look into the pollen, let me have the arrow over here. Yeah. Can I move the arrow? Yeah. I think in here, what we have in here, I think this also looks a little bit like air bubbles. So the mounting medium apparently did not allow for the air to escape properly. Okay. So, so that's a UKIT. Usually UKIT is used for mounting histological specimens, like, for example, tissue cross-sections and so on. It's a very popular mounting medium, of course, because it dries quickly. What I heard is that people who are mounting histological cross-sections for anatomical observations, they often use UKIT. And but for pollen, as we can see, looks very different. And if you just compare now the reflections with the air bubble over here, so indeed it appears like there seems to be quite a bit of air inside the pollen. Yeah? So I'm just going to show this to you first, and then I would like to show you the whole thing, of course, also using the filters. So the next one is Uprol, and that is the mounting medium that is often used for insects. Okay, normally it takes 6 weeks to dry. Yeah, again very blurry over here. Yeah. But you see, again a little bit different. Yeah. There's still the air bubbles in there. A little bit, yeah, but yeah, it seems to make the specimen more transparent. I mean, that's also something that we've already seen before with insects, yeah, that they also become more transparent, and here as well. So yes, a comment. I'll soon have the opportunity to get entelan as a mounting medium. Do you have any experience with it? No, unfortunately not. I know that entelan seems to be a very popular mounting medium, but I do not have any experience with it. Yeah? Unfortunately, I would be happy if you could report back. Yeah, and what I generally would. So overall, what I would say is that it's maybe a good idea to have different mounting media around, so that you can always trial and error, because not every specimen is suitable with every mounting medium. Okay, so that it was now Uprol mounting medium. Let's move on. The next one is, yes, the dry mount. So here, no mounting medium or just air, and this is how it looks like. So that is the most native, so to say, yeah, and very difficult to focus. Why is that? The reason is because many of the pollen grains are stacked up on top of each other. And if there's a mounting medium, you can kind of press it flat. Yeah. So, but that is essentially the most native one. Again, I don't have my flashlight here, but you could actually illuminate them also from the top. Yeah. There is some dust and dirt as well from the collection of the pollen. I think, if I remember correctly, these are spruce pollen. Yeah. But I'm not quite sure. That was a couple of years ago. Yeah. Next one is now the PVA glue. Again, this here is water-based. Yeah, so, and look at this. Here we have also maintained the original shape quite well. Yeah, that's that's the PVA glue. Yeah, you see also that they seem to be a little bit larger, because I think if you use the other mounting medium, they start to shrink a little bit. And the last one that I would like to show you is, I would say, maybe the least suitable one. That is clear nail polish, and I say least suitable because there are lots of bubbles. And as the nail polish dries, it starts to shrink quite a bit. And so what we have here on the side is you see actually that's the bubble, yeah, and you see that over here on the side you've got the pollen grains. Yeah. But interesting here, with this one you're able to see the surface texture again much better. Yeah, the surface texture of the pollen, yeah. So we can again play around a little bit with the, yeah. So, and what I would like to do now is, I'm going to put it now over into my other microscope, and we're going to have a look at these things now using a different using darkfield. Okay, so let me take it out again, and I also have some water samples prepared as well, so that we can look at a few live organisms. I have to tell you the following: when planning this session today, I'm always thinking, okay, what could I talk about? Over 1.5 to 2 weeks ago, I actually started to make an enrichment culture for Paramecia. So I've got several water samples, and I dropped a small wheat grain. You crush a wheat grain between 2 spoons, and then you drop it in there, and then you should have a lot of ciliates, Paramecia, and so on. It always worked, but this time not at all. And I think the reason could be that there might be some water crustaceans, water fleas in there as well, and then they have eaten them up, so I have to restart again. Yeah. Yeah, I've been using PVA glue to mount samples, but when it dries, the glue makes the samples look almost like frosted glass. Is there something I could add to the glue to make it clear? You have to use clear PVA glue. There is the PVA glue comes in the form of a white glue. Okay, like wood glue, it's called PVA glue, but this glue that I have over here is completely clear and transparent. And that's the one that I'm using. I added a little bit of water. I took out a sample into a separate container, mixed it with a few drops of water to thin it down a little bit. Yeah, now, but that is the one that I'm using over here. It says here natural ingredient school glue, yeah, washable, child friendly. Yeah. And the wood glue is the white one, is also a PVA glue, but that's not the one I'm using. Very often, if specimens turn cloudy, and this can happen quite often when you're mixing a moist specimen, one that contains some water, with basically a resin-based mounting medium like U-Kit, U-Pearl, and so on. Then what will happen is that the water is not able to evaporate, right? And then you have little tiny water bubbles inside the mounting medium, and then this causes the clouding, so to say. Yeah? So this is a little bit the issue here. Yeah? I think I've heard of some scientists modifying the DNA of some organisms. Sure, I have done that when I was at university. Do they go into the cells, take a sample, or someone modify the DNA? If so, how? That is a huge topic. Generally what you do, I mean, there are now modern ways, CRISPR-Cas9 method and so on, but generally what you do is the following. If you want to add some new DNA to bacteria, because it's what you often do, is you just mix the DNA using a pipette like this one, yeah, with some bacteria. Liquid is mixed with liquid, and then you do a so-called a process called electroporation. It's called you electroshock the bacteria, and this will cause most of the bacteria to die, but some of them will actually take up the DNA, yeah, through the cell membrane. Yeah? And if a few of them survive, then you are able to reproduce those bacteria. So actually putting DNA into cells is not so difficult. Plant cells, scientists have actually used a so-called a DNA gun. You can use that. DNA gun basically shoots DNA into the cells. You basically put the DNA on gold dust, because gold does not react, and so there's DNA sticking on the gold dust, and then you're using a so-called DNA gun, and you're shooting the gold dust into the cells. Okay, so there are plenty of methods, which basically I've used some of them. Yeah, and I've not used the DNA gun, however. Before I forget, let's do this here. So yeah, the whole thing about molecular biology and DNA and stuff like this is quite fascinating, but not possible to do at home, because it's not a good hobby science thing, because equipment too expensive, and it's also very tedious work. Very often things don't work out right away. Yeah. So we are now back in darkfield, and I'm going to make it a little bit brighter here. This is, oh wow, I have to turn up the lamp, of course. Yeah, so that is now, these are now the pollen grains used in glycerol, okay, or glycerin, okay. And you can again see that there is a little bit of, honestly, on camera the effect doesn't look quite as good as when you're looking through the microscope, yeah. But again, you can optimize the filters a little bit. Yeah. But that's basically how it looks like. Yeah, the glycerol one. And let's go through the whole thing. Yeah. And let's try the next one, U-Kit. In case you're kind of wondering why I've chosen pollen and why I've done the test series, the reason is because spring is coming, or we're starting off here in Central Europe, where I am, and I want to make some pollen slides. And normally what you do is, for mounting pollen, you use glycerin gelatin. According to Kisser, there are two versions, according to Kaiser, and glycerol gelatin according to Kisser. And and I just wanted to also try the other mounting media. So that is what a U-Kit. And you see, look how this looks like. Yeah, the pollen looks shrink shriveled, right? And it looks very different. Yeah? But, and that's the good news, we're still able to see them quite nicely. Okay, in contrast to the water flea, which was so transparent. Yeah? And here again, we have to go down a little bit, and here, yeah, go down again a little bit. Now we are able to see again a little bit better, yeah, the oblique effect. Okay. So again, a comment, I'm using clear PVA glue, but I will try to add some water to dilute the glue. Maybe it's the glue brand I'm using. I can't find Elmer's in my country. Thank you for the suggestion. Yeah, it's a trial and error. I bought the Elmer's glue over Amazon. I'll be honest with you, and it was pretty cheap actually. Are you going to show us your electricity-inducing gadget one day? Maybe you said you have one during the nematode live stream. Yeah, so that is the thing that I bought myself some time ago, a power supply unit. And with that, you're able to make, I think, voltages up to 30 volts. I think over a year ago I already did a live stream where I showed it to you, because paramecia are able to move along the electrical current. And yeah, that's actually something that I might try. Thank you for the suggestion. I almost forgot about it again. So maybe the nematodes or other water microorganisms are also going to respond. Yeah. So I'll go down into the cellar and dig it out again. Yeah. Yeah. So, yeah. Okay, yes. Yeah, yes. That's another thing. When making mounting media, there is always, of course, the problem that sometimes there are bubbles in there. So, indeed, applying a vacuum is actually, it would be quite useful. Okay, a vacuum chamber. Yeah. So, in one of the previous videos, I've showed some video clips from a viewer, Hadrian, who's basically made one. Okay, so there was UKIT, and we can see that it looks very different. So let's go UPROL. Okay, and yeah, and again we are able to see that here. Let's focus again. Yeah, you see that here the 3D effect is yet a little bit stronger, I think. Yeah. So let's close it, and let's turn up the light. Yeah, and I have to turn up the light quite a bit in order to see it. You see that some mounting media, like UPROL, make it more transparent, and then it's not quite as reflective anymore. Yeah. So I think what we can see quite nicely is that if it seems to be quite transparent, then we might get a better oblique effect. Yeah. But maybe not such a strong dark field effect, because it's not able to reflect the light quite as much. Let's go up to 40 times. Let's see this. How I always have to refocus a little bit. Yep. Okay. Yeah. I don't know. Adjustment is. Look, there's another thing. Yeah. Here we go again. Yeah. This is now. Yeah. Focusing. Yeah. So now you actually see again, the slight 3D effect, and again some air bubbles on the bottom. Yeah. So, and last but not least, let's go back again here. I still have a few. Now the dry mount. So bottom line is, there is probably not one single perfect solution here. So that is the dry mount, basically surrounded by air. That's how it looks here. Let's turn it down a little bit. Because the pollen are stacked up on top of each other, it's more difficult to focus. Let's open it again. Let's see how if we also are able to get somewhat of an oblique effect here. Not quite as nice. Okay. And there are two more. The next one is the PVA glue, and then a nail polish. That's the PVA glue. I think it's still one of the nicer ones. Yeah. It's the PVA glue. Because it is water-based, yeah, it's compatible with the pollen, because the pollen will absorb the water. They might swell a little bit, yeah, and then yeah. And let's open up. Okay, that's the so let's open up this again here. It's too bright. Yeah, and but for the oblique effect, not quite as much. Yeah. See, yeah, I don't get a very strong oblique effect here compared to the one for Uprol, for example. Yeah. And the last one, that is the nail polish. Okay. So let's try darkfield again. Bright. A little bit. There's a second here. Yeah, the condenser was not yeah. This is how this one looks like. But again, here, even here, it's interesting. Even here, we are able to see the surface texture of the pollen better. Something I was not able to see. Yeah, if you look at the pollen, you see that there's a little bit of surface texture, which maybe is a little bit better visible over here. Yeah? I would like to fixate some crystals. What should I use to make a permanent slide? The urine crystals disappear again, maybe because of the water in the air. Interesting. So what I would suggest is the following. If you put a mounting medium on crystals, then the liquid in the mounting medium, depending on the crystal, but the solvent might actually dissolve the crystals. So what I suggest is the following, is that you actually make a dry mount. Like this over here. What you do is you make a ring using a slide ringing table, or if you watch one of my previous live streams, I showed how you can do that. And then you basically put a drop of the liquid on here. You allow the crystals to form, the water to dry, and then you put a cover glass on top again, which you also glue on with some nail polish. So the blue ring that you see here, that is nail polish, right? So what you have is essentially a dry mount of the crystals, and very often this will actually look quite fine because the crystals and the surrounding air, there's a large difference in refractive index again, which allows you to see it better. Yeah? So is it easily possible to approximately determine the size or diameter of a pollen grain? Thank you for asking, because this is actually something that I was also thinking about of doing and showing. Just a second, I will use the PVA glue again here, and I need to reach down now into. No, I'm going to use the other microscope here. I'm going to reach down now into my drawer. And I'm going to now show you how you can determine the size of those pollen grains. Okay. Actually, I was thinking about making a complete video, live stream rather, about this. Where is it? Here it is. Here it is. Okay. So maybe I have to. You know what I'm going to do? I'm going to just change over the camera, hoping that it won't stop working. Let me check. I'm going to now move it over to my other microscope. Okay. And the top camera stopped working. Isn't this nice? Somehow always does that. Let me quickly do the following. Stage cam, deactivate it. Now it should be gone. I reactivate it, and I hope that it returns. And here we are. Sometimes, for whatever reason, it stops working, but here we are, okay? So that is now the pollen slide, the one that you see, other side over there, right? Okay. And what I need to do now is the following, is I'm going to show you something that I have here. This is also something that I bought some time ago, which is a so-called a micrometer slide, because you wanted to know the approximate size of those grains. So I'm going to show you how this works, right? I don't know if you're able to see that, but there are some etched on here. There are some scales, right? And what it says here is a calibration slide. One division is 0.0 1 millimeter, so 10 microns. 10 microns is one division. So I'm going to show you now how this looks like, and then at the same magnification we're able to see yeah, the size of of a pollen grain. Yeah? So okay, yes. So what I'm going to do now is just watch what I'm doing here at the top again. I'm just going to add this slide here. Okay. And yeah, let's move the whole thing. And now the difficult part is I have to find it. Oh, okay, that's the thing. Yeah, see, there's dust and dirt. So what I have to do now, this is now using my 20 times objective. I'm gonna go down all the way to the low power. Okay, simply so it's easier for me to find what I want to look for. Lots of dust and dirt. Was there something here? Here's something. Here's a line. Here's a line. It's a dot. No. Yeah. Here. What does it say here? The diameter of the dot is 0.15 millimeters. Let's see. The diameter is 0.07 millimeters. Where is this one? I don't know. This is not the one I want to. We're already at the end. Okay. Let's have a look. One division, that is 10 micrometers, 0.01 millimeters. That's the one I want to have. Okay, who cares if it's upside down? Okay, so one division is 0.01 millimeters, which is 10 micrometers, which should be the approximate size of a cell, of a eukaryotic cell. So here we are. So that's how it looks like. And one division means basically two adjacent lines. I'm using the 4 times objective, so I have to really zoom in. It's 10 times. 20 times, of course, I have to go up with the brightness a little bit. Okay. Okay, here we go. Yeah. And 40 times. Okay. So, and those pollen grains are huge. I just want to inform you. So basically, yeah, this is one division here. Okay, so one line to the next line is 0.01 millimeters. Okay, so 10 of them must be. It's basically a tenth of a millimeter. Okay. Yeah, so, and let's now have a look. If this is basically just, I don't know, let's say the width of my arrow, okay? The width of my arrow over here right now goes approximately from one line to the next line. Okay, and now let's go and find a pollen. And let's focus a little bit here. So, yeah, let's just use this pollen grain here. You know, how many times across? Maybe 5 times across. Okay. So yeah, 0.01 millimeter times 5 is around 50 micrometers. 50 micrometers. Okay. So this is kind of, yeah. So if the width of the arrow, yeah, is 1, 2, 3, 4, 5 approximately. Yeah. So this is about 50 micrometers across. Yeah. So this is yeah, it's already pretty large. Yeah? Have you ever tried mineral oil as a mounting medium for things like crystals? And the answer is no. And the reason is that there was no need up to this point for that. You cannot, if you use any liquid mounting medium, then which does not turn hard, so, which does not turn solid, then of course yeah, it's difficult to make a permanent slide, right? So one would have to actually see if decreasing the refractive index between the crystals and the surrounding yeah, medium actually improves something. Yeah. So mineral oil you can try to use, or kitchen oil, or even immersion oil can be used as well. Okay, but let's just, I forgot to flip up the condenser here. Huh? Yeah, so, and I don't know where the yeah, that's again the circle over here. Okay, and here we are again. Yeah, with yeah. There are also special slides around called hemocytometer slides, which allow you to actually count cells. Yeah, so this was simply a little bit of a how do you say, a sidetracking here. I think I do have a measuring device in the camera software I have. It kind of gives the distance in micrometers as I draw lines and stuff on the screen. Yes, that is correct. However, you have to calibrate this, right? And generally, it is also possible to calculate the approximately the magnification and so on. But this is difficult because you have to include also the magnification of the camera optics and all of these things as well, right? And for this reason, it's usually it gives you a much more precise and accurate measurement by using a direct measurement. Yeah, you can also actually put a ruler, really a ruler, under the microscope, and then using the low power then to also calculate the magnification as well and the size. But I think I'm going to save that for another live stream. Okay. So this was basically the micrometer slide, and what I would like to do now is, for the next 15 minutes or so, okay, basically, imagine having a pointer with a scale on it. That's actually a cool idea. That's actually a nice idea. So if you have, for example, over here, a pointer like this, with a scale on it. But then I'd need, for each magnification, I'd actually need a separate scale. Okay, because but that's actually not even difficult to do. Thank you for the suggestion. That's actually something. What I could do then is I could put all of the scales maybe somewhere in the corner for the different magnifications, and then I can just use that. I want my commission. Yes. Okay, that's a nice idea. And as a matter of fact, I did already start to do something like this, work with scale bars. But I think that's certainly a good idea. So next thing that I would like to do is I'm going to carefully move those permanent mounts away because they might not be fully dry yet. And I would now like to do the following, to look at some water samples using oblique, dark field, and so on. Because sometimes people want to see a few living things as well. So let's have a look at this here. Again, I actually was hoping to make to observe some paramecia, but unfortunately, they didn't grow or they were eaten up. Okay, so that is basically now a water sample at 10 times, but however there was, ooh, look at this, very nice. So what do we have here? This is important, not important, I think that's interesting. What we see here are bacteria, okay? And then we're going to see how well we are able to see those using dark field. So basically this is now in DIC. I'm going to now show you, this is now in bright field. Okay, you still are able to see them. Let's move the arrow out of the way a little bit. Okay, so in bright field, I'm still able to see it, and I'm using now the 20 times objective, 40 times objective. But the thing that I would like to really illustrate here is the following. You see this especially at a low power. Do you actually notice? Or you know what, I'm going to switch over to phase contrast. Okay, that's now phase contrast, okay? Phase contrast is, as you probably already know from my previous videos, that phase contrast is really the way to use for observing bacteria. And look what happens here. Those little dots that are floating around are bacteria. There are a couple of them floating around here. And look what happens. All of a sudden, the concentration really goes up. Okay, and if I were to wait now, what's going to happen is most likely the bacteria are going to start to move downwards or upwards. And so this band or this front of bacteria is going to start moving collectively. And you see this very often in water samples that have bacteria. Sometimes there are a few of them scattered throughout, and then all of a sudden, they seem to start to aggregate like this, and they start to collectively move into one direction. And what they're doing is they're following the oxygen gradient. because there is more oxygen at the edge of the cover glass, and that's why they're moving towards that collectively. Yeah, and sometimes you can also see those bacteria also gather around green material like algae and so on, because they produce a lot of oxygen. Okay, so and yeah, so this is basically the way that it looks like in phase contrast. Let's do it again over here. Same magnification now here in bright field. You see, they're much more difficult to see. Yeah, and DIC. Okay, so now let's have a look. Let's have a look how this actually, or I have to admit I have not tried this yet with darkfield with the microscope here, but let's try this, okay? That's a lot of bacteria. Do you think that the sample is decomposing? Of course. That's what bacteria do, at least many of them. Huh? So that's the thing, yeah? So this is, following the oxygen. That's amazing to know. Yes, that's a very common observation. Yeah, you sometimes see also lots of bacteria. By the way, that's also one way that you can actually determine whether something is producing oxygen or not, is to see if it's able to aggregate bacteria around it. Okay, so let's have a look now if we're able to see I don't know if you're able to see it on YouTube as well. But let me turn the here it's better again. Yeah. So let's now put the whole thing now into darkfield, other microscope, and I don't know if it's gonna be successful or not, but let's try it. And I have to focus and find it. I don't know where it is. Maybe there's some bubbles here. I don't know. So let me, because it's now just a question of finding it. Maybe at a lower magnification, because some of the cover glass has already dried out. Let me quickly check. I'll take it out again and see where the sample. Oh, it's over there in the other corner over there. Okay. So over here. Yeah. Okay, a worm. Okay. So, and here they are. Okay. What's this over here? It's a nematode worm next to the bubble. But let me see. Let's go a little bit higher with the magnification. Yep. And this is now basically again, the front of the bacteria, which should be slowly moving into one direction. Sometimes in time lapse you can actually see this quite well. So this kind of illustrates a little bit the following. I'm going to just show you the following. I'm going to now remove the filter. It's bright field. I'm going to close the condenser, and I'm using the 10 times magnifying objective. Okay. Close the condenser, turn down the light a little bit, and you see how the bacteria look like. You are still able to see them, but the contrast is not very high. Yeah, this answers a little bit the question, because people would like to know always what magnification do you need to see bacteria, and this I'm using on my 10 times objective here, so you don't need a lot. 40 times, I need to Yeah, that's how it looks like. Using 40 times, it's also pretty well visible. But with 10 times again, but with the dark field in place, and opening the condenser again, then you're able to see them at better contrast. Okay. And and that's a nematode worm again. Yeah. I think the camera where we can see the objectives stopped. You mean this camera over here? No, it did not stop. It's pointing to the other microscope. Okay. Okay, but thank you for reminding me. Okay, so this camera over here is still working, but it's the other microscope. I switched microscopes, but I did not change the camera. Okay, yeah. But thank you for reminding me. Huh? So yeah. So this is somebody was wondering how you were doing this without a slide. Okay, yeah, I got it. Yeah. So okay. I'll be changing the thing now. Just a second. Okay. Yeah. So that's basically now the correct. That's not the correct slide. Okay. Yeah. So now here we go again, right? Yeah. So this was kind of a so my suggestion is because of my previous videos that I've made. That's actually one of the reasons also for this live stream. I've sometimes demonstrated phase contrast and people immediately wanted to upgrade their microscope to phase contrast. Then it's not always possible and it's expensive and so on. And I'm trying to say it's not necessary. Before you do any expensive upgrades or buy yourself a new expensive microscope, try playing around a little bit with those homemade filters. Yeah. Can you go higher magnification in dark field? Yes, but I'm not quite sure whether the filter is the correct size. Okay, and yeah, that's higher magnification dark field still works. You see, the thing is the following: the image quality really drops down. Okay, the reason is because at a higher magnification there is much less light. Okay, oops, I've bumped into the filter. There's much less light, and then the camera has to expose more. It has a higher gain, and then it becomes more and more fuzzy, right? Yeah, but that's now using the 40 times. And if I open it yet further and go down with the light, then I should have oblique illumination. That's oblique. Okay. That's oblique illumination now, where you see that. You see, I sometimes I think that look. If you look at this here right now, the image does not look quite as, under quotation marks, clean. The reason is that those bacteria that are out of focus, they will still kind of create a little bit of a fuzzy, blurry image, right? And this kind of disturbs the image quality a little bit, yeah? So when they're only those that are really in focus are actually dots, all of the others are kind of making this kind of cloudy, fuzzy appearance. But in oblique illumination, yeah, you don't see that so much, and you are getting a more flat image. And those bacteria that are out of focus, you do not see them at all. Yeah, so that's simply some Oh, look at this. This is not a ciliate, it's a flagellate, because it has this one flagellum in front. That's a eukaryote. It's also quite nice. But there seems to be this dirt in the optical system here a little bit. This black thing in the middle here, we just ignore that. Yeah. Yeah. But here again, if you look at this one, you see that it's actually dark on one side and bright on the other side. Yeah, so yep, it's kind of moving around and probably also hunting down its food. Yeah. So a lot of things are happening. Yeah, this was basically just an old. Oops! Now my camera switched off and switched on again. That's interesting. Maybe it has this 30-minute timer in here. It's kind of it was switched off and then switched on again. So lots of stuff happening. Yeah. And let's have a look again, completely on the bright field. And in this case, you close the condenser. And now you're seeing the whole thing's a little bit more flat. But you're able to see the colors also a little bit better this way. Is this an amoeba over here on this side? Is it moving? I don't know. Yeah. There are special dark field condensers to buy which are not cheap. What is the advantage over patch stop? Yes, the dark field condensers have a significant advantage. What they do have is they have inside assuming that they're made like that, okay? I mean, maybe it's just a special condenser which also only has a flat disk inside, but the real dark field condensers, what they have is they have concave mirrors on the inside which actually redirect the light. What we're doing here with the patch stops is we're blocking out the light, right, from the center, so we're losing light. But with those special dark field condensers which have this curved mirror system on the inside, the light is simply redirected. So you're actually getting, also at higher magnifications, you're getting a much more brightness, of the image, because what we've seen here is we're going up with the magnification, and I just have to show you here, just very briefly. If we are using a higher magnification in order to get a darker background, we need to increase the size of the disk in the center. So the higher magnification, we have to use a larger disk in the center, and we already have less light. So there are two factors that take away light. Right, if we do not have a sufficiently large size of the disk in the center, then the background won't be dark. And that's a disadvantage. So dark field only practically works well, maybe up to 20 or 40 times. But if you want to, what happens if you want to have dark field with yet higher magnifications? It's going to be so dark that you're not able to see anything. Because there's almost nothing left for the light. Right, and for this reason, there is special dark field condensers which have the concave mirror system on the inside, kind of round mirrors that kind of redirect the light. But then again, maybe it depends a little bit on the dark field condenser that you have, but that's actually the ideal system here. So, have you seen a spiraled oval shaped eukaryote? I've seen so many of them. Spiral shaped. Well, many spirochetes are bacteria which are spiral shaped, but I see no reason why. Asymmetric ones. There are plenty of. There are lots of microorganisms around, single-celled microorganisms around that have unique shapes. So that's basically again the bacteria. And in dark field, again, let's do it like this. You have to open the condenser again. What time is it? Ooh, it's already slowly time again. And that's how it looks like here in dark field. And again, you see it's kind of a little bit not quite as clear at a low magnification. That's what we see here. Again, if you look through the microscope, actually looks pretty good, really. Much better than what you see here on camera. I love the moon landscape effect. Oh, that's an interesting analogy here. Of oblique illumination and with a colored plastic on top of the light. So much fun. I'm going to make a multicolored ruler to move manually over the light. Let me try the following. I don't know if, instead of using now the dark one, let me use the blue one. And then I think I'm just going to call it quits for today. Again, I'm going to change now the filter. So I'm putting in the blue one now. And that's now the blue one. Okay. Yep. Yeah. So that's basically now it looks also, the thing is, it also looks a little bit better because there is now less contrast. So we do not see the disturbing fuzziness of those bacteria that are out of focus. Last comment. I think that's also something that I would like to mention here. And then I'm going to call it quits, is the following. With dark field is so sensitive to dust and dirt that apparently it is even possible to see viruses using a dark field. Now, viruses are way below the resolution limit of the microscope. So what you're actually able to see is you're still able to see particles that are that small. However, you're only able to see it as a fuzzy dot. So you're not able to see any structural details, of course, but you're just going to see that something is there. It could be a virus, but it can be any particle of that size, right? So this is also interesting to see that dark field allows you to actually visualize things that you normally would not be able to see simply because it increases the contrast so much. But still, even though it's below the resolution limit, you're still not violating Abbe's law, which basically sets the limit of resolution because we're not able to see structural details. So it's basically we're seeing a fuzzy spot which is larger than the virus. in other words, right? For those of you who are a little bit into astronomy, if you put a telescope to a star, and if you really magnify it, you're also going to see a disk, but that's called a so-called an airy disk. It's just a diffraction pattern, but it's not really the size of the actual star that you see. Yeah? So I've gone a little bit technical right now. Yeah, but yeah, so that's basically explains now hopefully also that, yeah, even with 10 times magnification, you're able to see bacteria. Yeah? Okay. So, suggestion, could you consider putting the fluid from your eye under the microscope, please? I watched the shorter video of your saliva, so I thought of looking at it. Honestly, after you've requested that, I tried to do that, but I could not collect enough fluid from my eye. Okay, yeah, so I'm still working on that, but I have to somehow, maybe using some onions or so, I can maybe get my eyes to water. Okay, but you know what? I'll make a short video of that. Yeah, Abe's law. Yeah, that's basically yeah. Abe, he was working at I think at the Zeiss laboratories back in the 19th century. And Abe, Ernst Abe was his name. He set the theoretical foundations for microscopy. So basically, his formula said that there is a certain resolution limit to a microscope. So there is a certain resolution that you cannot go beyond with a microscope because the wavelength of the light limits the resolution. Yeah. Basically. The Abe's law, Ernst Abe, he basically is super important in light microscopy because he sets the theoretical resolution limit. And yeah, the thing is that many beginners, I would say, think, well, if you want to see something under the microscope, just go up with the magnification, just make it bigger, right? But there's no point in making something bigger because it simply becomes bigger but more fuzzy, so you're not able to see more. And this is basically what Ernst Abe has calculated. What is the limit? Yeah? And over here, just also for you to show, if you see that there's this number over here, the 10 times magnification, right? Then maybe you're able to see it over here. Do you see over here the 0.65? That is the numerical aperture. And you can put this number into Abe's formula, and then the result is what's the smallest distance that you're able to see under the microscope at a certain wavelength. That's theoretical stuff, yeah, not super important for amateurs. The 0.17 is the thickness of the cover glass, and the 160 is the mechanical tube length. That's kind of the standard. Yeah? But the number here, the 0.25 or 0.65, that determines the resolution of the objective. Yeah. So that's basically, yeah, I wanted to show. If you tuned in a little bit later, we're now looking at bacteria, and I just wanted to demonstrate a little bit of how those bacteria now look like in dark field. And right now I'm just using a filter, and by shifting it over, reducing it, here then we have again a little bit oblique illumination, which is something that I just showed you. Now I'm not able to see it very well for whatever reason. Okay, people, I think that's enough now for today. Again, 1 hour, 18 minutes. If you were joined in for the first time, I want to say please do consider subscribing, of course. I would like to invite you every week, usually on a Saturday at this time. If for whatever reason it's not possible on a Saturday, then it will be on a Sunday at the same time. Occasionally this happens, and I will give you an announcement in advance if this actually if I have to move it. I'm going to call it quits for today. Hope that you liked it. I've also do visit my other microscopy channel, Microbehunter Microscopy, which is a little bit more technical. Today I uploaded a video about phase contrast, which you might be interested in. And I wish you all the best. Happy microbe hunting. As always, see you around next week, I hope. Bye-bye. All the best.